Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over how to find the answer or find the delta H of combustion of a given reaction using Hess's law, where we are going to add equations together. We're going to manipulate them, add the equations together, get the resulting equation, and then use Hess's law to get the sum of the delta H's to get the heat of combustion. And then we're going to use some gas laws. So there's two parts to this. There's an A and a B. Right now I have A on the board. And then after I finish A, I'll do part B. So let's get into this. So here we have acetylene gas. That's H2. That's C2H2. Gas is used to fuel. Is used as fuel. As a fuel in welding torches by combusting it to produce a very hot flame. Its balanced combustion reaction is shown below. So here we have our balanced reaction. So the acetylene gas is reacted with oxygen. So we have 2 moles of acetylene gas reacting with 5 moles of oxygen to produce 4 moles of carbon dioxide and 2 moles of water. And so we want to find the heat of combustion for this reaction. And so they're telling us in part A, calculate the delta H, the standard delta H of this combustion reaction using only the information given below. So the expectation is that we need to manipulate these equations using the rules that are associated with the balanced equation and the heats of enthalpy of those equations. Remember that if you flip or reverse a reaction, then you got to change the sign of the enthalpy of the reaction. Also, if you multiply the equation by some factor, then you got to multiply the delta H of the equation by that same factor. And finally, Hess's law, if you add up, if any given equations add up to a resulting equation, then you add up the delta H's of those equations to get the delta H of the resulting equation. So that's what we're going to do. So let's get started. So this is our target. So we want to pay attention to what's in the reactant side, what's in the product side. And we're going to have to look at these equations to see what we got that's going to help us. So, okay, so let's start with the reactants. So I have 2 moles of acetylene. So I want 2 moles of acetylene here. So where do I find acetylene? So you'll see in equation number 3, we have acetylene gas as a product, but we don't want it as a product. We want it as a reactant. So we're going to have to flip this one. So let's go ahead and flip this one. So number 3, we're going to have C2H2 gas plus CaOH to aqueous, and that's going to give us CaC2 solid plus 2 water, 2H2O liquid. And so now, since number 3, that's going to be a negative 126 kilojoules. So we got to change the sign because we flipped the equation. So then we're going to call this delta H5. And that's going to be equal to positive 126 kilojoules. So we're going to just get rid of this. Since we flipped it, we don't need it anymore. Now notice here that I have 1 mole of the acetylene, but I need 2 moles of acetylene. So I'm going to have to multiply this by 2. So I'm going to multiply this equation by 2. So that means I'm going to have a 2 here. 1 times 2 is 2. And then 1 times 2 is 2. And then 2 times 2 is 4, which means then I'm going to have to multiply this by 2. So that's multiplied by 2. So now I've got 2 moles of acetylene that matches the 2 moles in my target reaction Okay, let's go ahead and go to the oxygen. I need 5 oxygen. Where do I have 5 oxygen? I have 5 oxygen here. Do I have oxygen anywhere else? No. So here I have 5 oxygen that matches the 5 oxygen gas. So I'm going to keep this just the way it is because now I can add this and this together and I'll have my 5 oxygen in the resulting equation. Okay, so this we're going to keep the same. Okay, so I'm going to draw an arrow to indicate that we got this from number 3. Okay, so now we've got our reactants ready. Now let's look at our products. So I have 4 carbon dioxide. Notice I have 4 carbon dioxide here that matches. This is on the product side. This is on the product side. So this is good. Okay, do I have any carbon dioxide anywhere else? I have carbon monoxide. No, nowhere else do I have carbon dioxide. So we're going to keep this, again, oxygen on the same side, on the right side, or left side, I mean, but correct side of this equation. Carbon dioxide, the same amount, this on the same side as the target equation. So this is looking good. So I'm going to keep this the same as before, like I said before. And I need 2 water liquid. Where do I have water here? I have 1 water liquid here. Okay. And that's about it. So I have water on this side. Let me double check. Do I have water anywhere else? Oh, I have 4 waters on this side here. But I only want 2. I have 1 water here, but if I could multiply this by 2, I would then have 2 waters on the reactant side. I'd have 4 waters on the product side. Then the 2 would cancel out the 2 over here, and I end up with 2 on this side, which is what I want for my equation. So let's go ahead and do that. So I'm going to multiply this equation by 2. So I'm going to have 2 times 1 is 2, 2 times 1 is 2, 2 times 1 is 2. And so then this gets multiplied by 2. Okay. So far, so good. So now I have water, the amount of water I have 4 carbon dioxide. Okay, so now that I've set it up, let's double check to make sure everything cancels out except for the products and reactants that I want in my equation. So here I have 6 carbon graphite, and here I have 3 carbon graphite, right? I don't want to change this equation here, but I need to get rid of the graphite. I have the graphite on the same side, on the reactant side, but if I flip this equation, then I'd have graphite on this side. So let's go ahead and flip the equation here. So I'm going to have CaC2 solid plus CO gas, and that's going to give me on this side CaO solid plus 3 carbon graphite. Okay, so now I flipped it, which means that I'm going to have to get the delta H. I'm going to have to change the sign here. So this is, let's call this delta H6. That's going to be equal to negative 463 kilojoules. And so now I can cross this out because I don't need this anymore. And so just to be clear, this equation came from number 4. We flipped this. So now that I have this equation, I have graphite here on the products, and I have graphite here in the reactants. However, I have 6 on this side, but I only have 3. So I'm going to multiply this equation by 2 to get my 6. So then, let me get this out of the way. So 1 times 2 is 2. 1 times 2 is 2. 1 times 2 is 2. And 3 times 2 is 6. Okay, excellent. Now, don't forget that if you multiply this equation by the factor of 2, then you got to multiply this by a factor of 2. Okay, excellent. So now the 6 graphite here on the reactant side is going to cancel out with the 6 graphite here. Again, we're going to add these equations. So the equations we're trying to add together is this one, and these two. So these two up here, these two up here to get this one. So we want anything that's not in this equation must cancel out. Okay, so we got the 6 carbon graphite cancels out. Okay, we've got our 5 oxygen. What else do we not have? We have 4. So carbon monoxide, I have 2 carbon monoxide. Carbon monoxide is not in this equation. So I have 2 carbon monoxide gas on the product side here. Where do I have carbon monoxide? I have 2 carbon monoxide as a reactant here. So that's going to cancel out. So that's going to cancel out there. Calcium oxide, I have 2 of them. That's not in my resulting equation. So this is on the reactant side. I need 2 calcium oxide on the product side. Here I have 2 calcium oxide on the product side, so that's going to cancel out. I have 2 waters here, liquid. That's going to cancel out with the 2 over here, liquid. So that's going to become a 2. So that's going to cancel out. Okay. I have 2 calcium hydroxide aqueous. I don't have calcium hydroxide here, so that's got to cancel out. Here I have it as a product. So I need 2 on the reactant side. Here it is. So 2 calcium hydroxide aqueous cancels out with 2 calcium hydroxide aqueous. Okay, looking good so far. I have my 2 acetylene gas. 2 acetylene gas, that's good. Here I have 2 calcium carbide. Okay, so here, that's not in my equation, so that's got to cancel out. So I have 2 over here as a product. I have 2 over here as a reactant, so that's going to cancel out. So this and this will cancel out. I have my 2 waters. This is gone, this is gone, this is gone, this is gone. So now I'm going to circle everything that's left. So I have my 2 H2CO2. Here we go. That's left. I have my 5 oxygen gas. So those are the 2 reactants. I have 4 carbon dioxide, 4 carbon dioxide. This is gone, this is gone, this is gone, this is gone. These 2 are gone. This is gone, this is gone. Here's my 2 waters to match with the 2 waters here. So carbon dioxide and water, and all of this is gone. So now when I add this together, everything cancels out except for reactants and products. So if I add this together, if I add these together, then I get 2 C2H2 gas plus 5 O2 gas gives me 4 CO2 gas plus 2 H2O liquid. And so the delta H of combustion is going to be equal to H1 delta H2 plus delta H5 delta H6, all of this together. And then when you do the calculation, you get negative 26 O2 kilojoules. And that is how you do part A using Hess's law and the relationships between balanced equations and their enthalpies of reaction. Okay, let's go on to part B. Okay, so here we have part B. So we're told that some of the acetylene in a 10.0 liter cylinder at 20.0 degrees Celsius is withdrawn and combusted under standard conditions in excess of air. As a result, the pressure of the cylinder falls from, where is it? Falls from 17.8 atmospheres to 16.0 atmospheres. How much heat is produced by this reaction with the amount of the acetylene gas that was taken out? And we're told to assume ideal gas behavior. So a couple of things, a couple ways you could do this. They're giving you the atmospheres of the gas, the amount of gas in the cylinder before you take anything out. And they're giving you the atmospheres, the pressure after you take some of the acetylene gas out. Now, they're giving you the temperature, they're giving you the liters, the volume of the cylinder. So, and they're telling you to assume ideal gas behavior. So, you could use the ideal gas law in a two-step problem, right? So you can take the volume, take the temperature, make sure you convert the temperature to Kelvin, and then take the initial atmospheres, plug all of that in, right? You're going to solve for the ideal gas law. So you have P, we could call it P1, right? So you could do P1 V1. This is before you make any change. So P1 V1 equals N1 RT1. Solve for the number of moles that you have with this amount of gas. So that would be N1 is equal to P1 V1 over RT1. Plug everything in, right? And then you could find N1, right? So you just need to make sure that you change this to Kelvin, right? So 20.0 degrees Celsius plus 273.15 is going to give you 293.15. And again, for sig figs, remember when you're adding and subtracting, your answer should have the same number. I forgot Kelvin. Your answer here should have the same number of decimal places as the least number here and here, right? So here we have 2 decimal places. Here, there's only 1 decimal place, so the last sig fig is in the first decimal place. So I'm going to put a line there just to remind myself that that is the last significant figure for this. Okay, so now we have the temperature in Kelvin. We can plug that in. We have the pressure in atmospheres. We got the volume in liters. Plug it in. Solve for whatever the number of moles were before you took any gas out. And then do the same thing, right? So then you do N2 is going to be equal to, and then you can put everything after, right? So N2, P2, V2 over R T2, right? So plug in the new pressure, the volume, the temperature, everything, get whatever the new volume, the new number of moles are. And then to get the moles that you took out, you would just separate, you would subtract, right? So this would be the lesser amount, right? So I take N1 minus N2 is going to give me the change in the moles, which is the moles that I burned. This is going to give me the number of moles that I burned, right? So this is one way you could do it, right? The other way is to understand, hey, everything is the same except for the pressure, right? So the volume of the cylinder is the same. The temperature doesn't change. That's constant. And so the only thing that changes is the atmosphere, but that changes because the number of moles change. So in this case, right, if I do my combined gas law equation, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. If I eliminate anything that's constant, then volume is constant, so I get rid of that. Temperature is constant, so I get rid of that. And what you notice is that change in pressure is proportional to the change in the number of moles. So all I need to do is find the change in the pressure, and that's going to be equal to the change in moles. That's going to give me the change in moles. So then what I could do, instead of doing this twice and subtracting, which is perfectly fine, you should get the same answer, just a little bit more calculations, more time consuming. What you can do is, well, if I have P1, V1, right? If I subtract these two, right, think about this. So if I take these equations here, it'd be like subtracting this from this. But again, let's say, so then N1 minus N2 is going to be, I'm going to subtract this from this, I'm going to substitute this, so it's going to be P1 V1 over R T1 minus P2 V2 over R T2. But since temperature and volume and R are all constant, I can pull that out, right? So then this is going to be equal to P1 V1, oops, not P1 V1, P1 minus P2 multiplied by, and then I could just make these the same, right? It doesn't have to be 1 and 2. So the volume is going to be the same on both sides. Temperature is going to be the same on both sides. So it's just volume, R and T. So it's going to be V over RT. Right? So here, the change in the number of moles is equal to the change in the pressure multiplied V over RT. So basically what's happening is here, change, I have delta N is going to be equal to delta P times volume over RT, which is the ideal gas law, right? So all I did was I have P, oops. All I did here is I have, oops, I keep writing an R. PV equals nRT. Well, I just put in the change in pressure times volume is equal to the change in number of moles times RT. And then I solve for delta N. So delta N ends up being equal to delta P V over RT. So this is just a long-winded way of just saying, hey, look, if I can find the change and calculate the change, plug that into the ideal gas law, and then you'll get the change in the number of moles, and the change in the number of moles is equal to the amount that you took out and burned, right? So that's all I'm saying. So a long-winded way. I hope this is helpful. You want to think about things like this, especially when you're doing calculations. If you can find a shorter way of doing it, then it might save you time on a test or something like that, save you time on the homework. But again, if you do it the two-step way, perfectly fine, perfectly fine. You'll get the right answer. So I'm going to go ahead and use the change in pressure times volume is equal to the change in moles times RT. So that's going to give me the change in moles is equal to change in pressure times volume over R times T. So then all I have to do is plug in the values. So here, the change in the atmospheres, is going to be 1.8. So that's going to be 1.8 atmospheres times the volume, which is 10.0 liters, divided by R, which is going to be 0.08206 liter atmospheres over Kelvin mole, multiplied by the temperature, which is 293.15 Kelvin. Again, underline the 1 here. So then when I multiply this, I get, let me calculate this, 0.74825, 0.74825 moles of the acetylene gas. So this is the change in moles, but remember the change in moles in our containers because we took that many moles out of the container. So this is the number of moles of acetylene that we took out and burned. Okay, so now we got to go back to sig figs. Remember that when we're multiplying and dividing, the rule is that our answer should have the same number of sig figs as the least number here. So here I have 2 sig figs, and the reason I have 2 here is because I subtracted, and remember the answer to the subtraction of this is going to be that when you subtract, the rule is that your answer should have the same number of decimal places. So this has 1 decimal place, this has 1 decimal place, so I have 1 decimal place here. So therefore I have 2 sig figs here. This has 3, this has 4, this has 4, so the least number is 2. So I'm going to underline the 4 because that's the second sig fig. I'll keep everything else to avoid rounding mistakes because I got to do more calculations. Okay, now they want to know how much heat is produced by this reaction using this moles. Now, I have the balanced equation from part A. I know the heat of combustion, and so now I can use the relationship between the moles of the substances and the amount of energy produced, the amount of heat produced. And so here I have 2 moles of acetylene produces this amount of heat. So I can use that as conversion factor. So now I can take the 0.74825 moles of C2H2 gas that was burned, and now I can use the 2 moles of acetylene to negative 26.02 kilojoules. And so let me bring this down lower since I'm not getting in the way here. So again, 0.74825 moles of C2H2 over 1. And now, since I have moles here, I'm going to put 2 moles of acetylene on the bottom. So 2 moles of C2H2 on the bottom. And I'm going to put negative 2602 kilojoules. So negative 2602 kilojoules of energy. Moles of acetylene cancel out. Now I have kilojoules of energy. And so now all I need to do is calculate. And when I do that, I get 973.48. So negative 9 73.48 kilojoules. So that's what I calculated. Again, I have two sig figs here. That's the least number. So then technically I should only keep two sig figs, so that'd be 9 and 7. So negative 970 kilojoules of energy is produced. Unless I made a mistake here with the sig figs, this is the right answer. So I hope this is helpful. So if this has helped you, if you enjoyed the video, if this helped you in any way, then please by all means like the video, share the video, hit that like button over here somewhere. Also, subscribe to my channel. Do me a favor, help me out. When you do that, click on the notification bell and then click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or question you need help with, put that down below. If you have a topic you would like me to cover, put that down below. I would love to hear from you. Thanks for joining me and have a great day.